Alright, so we've talked about the electron geometry, and basically what it boils down to is how many groups are around the central atom after you've drawn the proper Lewis structure. And so we came up with the basic 5 shapes. And I encourage you to look at lots of pictures of these or look at models of these. We have models in the lab, we have models in the lecture room. And so essentially, depending on how many groups there are around the central atom, remember that a group is a lone pair, a group is a single bond, a group is a double bond, and a group can be a triple bond. This will describe that electron geometry, the shape of the electron groups around the central atom. The molecular geometry, or molecular shape, can be a little more complicated. And it is a little more complicated if lone pairs are involved, if there are lone pairs on the molecule. For example, if there are 2 groups around the central atom, there's my central atom, and I have 2 groups, which means those groups are going opposite of each other in a linear arrangement. If both of those groups have atoms attached, I still call the molecular geometry or the molecular shape linear because the 3 atoms form a line. If there are 3 groups around a central atom, those 3 groups will take on a trigonal planar arrangement where the bond angle is about 120 degrees. If there are 3 atoms attached to each one of those groups, an atom attached to each group, I still call the molecular geometry or the molecular shape trigonal planar. And I do so because the shape that the atoms make is a trigonal planar arrangement with a bond angle of about 120. However, if there is a lone pair among those 3 groups, the 3 groups will still take on an electron geometry of trigonal planar, but if only 2 of those groups have atoms attached and the 3rd group is a lone pair of electrons, that lone pair takes up space. So here I've drawn it in the up position. There is a region of space occupied by that lone pair, but the molecular geometry or the molecular shape of the molecule is simply described by the shape that the atoms make. And that shape is not a trigonal planar. That shape is called bent or angular. When a lone pair is involved, it is somewhat invisible in terms of looking at the molecular shape of the molecule. The molecular shape only describes the shape of the atoms as they're bonded to each other. And so when there are 3 groups around the center, the electron geometry is trigonal planar. No ifs, no ands, no buts. This table is exactly the answer for all electron geometries. But if a lone pair is involved in a trigonal planar electron geometry, the molecular geometry is described as bent or angular because that's all I see when I look at the molecule, when I look at the position of the atoms. This lone pair is taking up space. In fact, it's actually taking up a little more space than the groups that are bonded to atoms, and that makes this angle between the 2 atoms attached to the center actually a little less than 120. You can still describe it as 120 degrees for purposes of this class, but it's actually a little smaller than that because this lone pair, which takes up so much space, is pushing down on it. If all 3 groups have atoms attached, they're all going to take up the space somewhat equally, but if there's a lone pair and 2 atoms attached, then that's going to push a little. But again, the molecular geometry is bent or angular. Now if I have 3 groups around a central atom, those 3 groups will take on a trigonal planar arrangement, no ifs, no ands, no buts. The electron geometry with 3 groups is a trigonal planar. If only 1 atom is attached and the other 2 groups are lone pairs, those lone pairs still take up space in the trigonal planar arrangement, but I would describe the geometry of this molecule, the molecular geometry, as the shape describing the 2 atoms that are attached to each other, in which case I would describe it as a linear molecule. Let's move on to 4 groups because I have so much fun drawing these. I encourage you to look at lots of pictures of these. 4 groups around a central atom is a tetrahedral. No ifs, no ands, no buts. These are the way we would describe the electron geometry about a central atom with that many groups attached. So 4 groups around a central atom takes on a tetrahedral electron geometry. If there is an atom attached in all 4 positions, I still call the molecular geometry tetrahedral because it's taking the shape of a tetrahedral. If there are only 3 atoms attached and a group of lone pair, one group is a lone pair, the lone pair is taking up space, and I could have put it in any of the 4 positions. I chose to put it up. That lone pair takes up space. It occupies one of the positions of the tetrahedron, but I describe the shape of the molecule, the molecular geometry, by the shape made by the central atom and the 3 groups attached, and I call that a trigonal pyramid. I encourage you to look at lots of pictures and models of this. What we have is we have a central atom with the 3 legs pointing down at the tabletop, and it sits up off the tabletop. This is raised a little bit off the tabletop, and so it's a pyramid that has a 3-sided base. This is a trigonal pyramid. It is hard to tell from my picture, granted. I encourage you to look at lots of models of these. All right, so 4 groups around the central atom. Electron geometry is tetrahedral. If only 3 atoms are attached and one of the groups is a lone pair, I call that a trigonal pyramid. Let's look at the tetrahedral again. And let's say, again, 4 groups around the center, tetrahedral, no ifs, no ands, no buts. But let's say only 2 atoms are attached. The other 2 groups of the 4 are lone pairs. And it doesn't matter where I put the lone pairs. I'm trying to put it where it's easiest to see, but I encourage you to go look at pictures of these things. Here I have my central atom, my 4 groups in the shape of a tetrahedral, but only this group and this group have atoms attached. The other 2 groups are lone pairs. And so I want to describe this molecule. The molecular shape in this case is bent or angular. Now a minute ago we said that we had a bent or angular in this instance. It is different than the bent or angular in this instance because the bent or angular up above had an electron geometry of a trigonal planar, which means that the angle here is about 120. We said it was a little smaller than that. This bent or angular down below has an electron geometry of a tetrahedron, so the angle here is about 109, 109.5. Again, it actually is a little smaller than that because of the lone pair, but it's the angle that we see on a tetrahedron. I forgot to put it over here, but this angle would be at about 109, 109.5. It's the angle we see for a tetrahedron. We could take this one step further. With a central atom and 3 lone pairs, meaning only 1 atom was attached to my electron geometry of a tetrahedron, I'd be down to simply a linear. So here we have examples of starting with a linear electron geometry. We have linear molecular geometries. That's really our only option, and we saw that up here at the top. With a trigonal planar electron geometry, we can have a trigonal planar molecular geometry if all 3 groups have atoms attached. We could have a bent or angular molecular geometry if we end up with a lone pair, or we could have a linear geometry if there are 2 lone pairs and 1 atom attached. With a tetrahedral electron geometry, we might have a tetrahedral molecular geometry if there are 4 atoms attached. We could end up with a trigonal pyramid molecular geometry if there is a lone pair, or we could end up with bent or angular if there are 2 lone pairs. I encourage you not to simply write these down and look back at your list every time, but draw them or make these models and see them. If you don't have a model kit at home, toothpicks and marshmallows work great for making these models. All right, let's clear some space and we'll work on the last 2 electron geometries. All right. If we have a trigonal bipyramid, it is because there are 5 groups around the central atom. Let me attempt to draw that. Again, I encourage you to look at pictures of these, look at models of these. If all 5 of these groups have an atom attached, we call the molecular geometry a trigonal bipyramid as well, because all 5 positions have atoms attached. However, if there is a lone pair, at this point we have a little bit of a quandary in terms of how we do it. Let me make another copy of this. Alright, if there is a lone pair, we run into, for the first time with this position, with this shape, the fact that the positions in the up and down are equivalent to each other, but they're not equivalent to the 3 that are around the triangle. The positions around the triangle are equivalent to each other, but they are not equivalent to the positions up and down. So whether or not there is a lone pair in the up and down position or in the triangular position, we call this an axial position in the up and down. We call it an equatorial position around the triangle, kind of like you're looking at it as a globe with an axis and an equator. These 2 positions are not equivalent, so whether or not the lone pair goes in one versus the other, that's going to give us a different molecular shape. Well, we don't get to choose what the lone pair do. The lone pair do what they're going to do, and then we describe it. And what we find is they do not go in the axial position, they go in the equatorial position. So if there is a lone pair, that means there would be 4 other atoms attached in this fashion. We have this geometry. This geometry can be called a distorted tetrahedron. There are 4 groups around the center. They do not take on a tetrahedral geometry, but some textbooks describe them as a distorted tetrahedron. However, I like the description better that if you turn it on its edge and look like this, what I've done is I've taken it and turned it essentially 90 degrees that direction. So I have this one coming forward and that one going back, we see back there, and then the across. But I'm going to put the lone pair, as long as the lone pair is on one of the equatorial positions, I'm going to put it in the up position and look at what the rest of the atoms make. This is often referred to as a seesaw. You remember the old seesaws or teeter-totters from the playground? If you have a model of this, it will tip back and forth like a teeter-totter, like a seesaw. Again, I encourage you to look at these, hold these in your hand. We've got some models in the labs as well as in the lecture halls, and you can always put toothpicks in marshmallows and it works out good. So I like calling this a seesaw geometry. This would be the molecular geometry when there are 5 groups around the central atom taking on a trigonal bipyramid electron geometry, but one of the groups is a lone pair, which takes up space, and it'll take up space in the equatorial position, and then the rest of the atoms take on a seesaw geometry. The molecular geometry is seesaw, or you can call it a distorted tetrahedron. Let's take it one step further. Let me draw the picture again. If there are 2 lone pair, the 2 lone pair are going to take up, again, position around the triangle, and the remaining 3 groups are atoms attached to the center. We call this a T-shape. If you can envision sort of twisting it a little bit, these make a T as they cross. Let me go back and fill in some information about the angles. Remember that in a trigonal bipyramid, we actually have 2 angles. We've got 90-degree angles this direction. We've got 120-degree angles this direction. And we still see those 90-degree angles and 120-degree angles here. We've got 120-degree angles here with the triangular shape. We've got 90-degree angles compared to the equatorial positions, or I'm sorry, the axial positions. When we get down to the T-shape, all we're left with is 90-degree angles. It's really hard to tell on my drawing. I apologize for my crummy drawing skills, but I encourage you to look at these, hold these in your hands as you look at these in the laboratory or in the lecture. One last to go with this guy. If there are 3 lone pair of electron lone pairs, they will take up the 3 triangular positions, the 3 equatorial positions, which means that the atoms attached will be directly opposite each other, and we will have a linear molecule. So an electron geometry of a trigonal bipyramid, because there are 5 groups around the center, Could be a trigonal pyramid molecular shape or molecular geometry if all 5 positions have atoms. It will be a distorted tetrahedron, or you can call it a seesaw if there are 4 atoms and a lone pair. It will be a T-shape if there are 3 atoms and 2 lone pairs, or it will be linear if there are 2 atoms and 3 lone pairs. Now let's do the octahedral to finish it up. Alright, for the octahedral, we have a central atom and 6 groups attached. Remember, these 6 groups are in the up, down, left, right, forward, back positions around the central atom, like a 3-dimensional grid system. And if all 6 positions are occupied by atoms, there are 6 atoms around the central atom, then the molecular geometry or the molecular shape is still called an octahedral. If there is a lone pair, now all 6 of these positions are exactly equivalent. So if there is a lone pair, it doesn't matter which of these positions I draw it in, and let me change it. Let me put it in the bottom position. If I put the lone pair here in the bottom position, that means the 5 atoms around the center would take up these positions. And to describe this geometry, we call it a square pyramid. It's a little pyramid with a square base. All the angles there are 90 degrees from each other, just as they were in the octahedral geometry. But it is now a square pyramid because I have a lone pair down here. If there are 2 lone pair, again I'm in a little bit in a quandary, because the 2 lone pair, depending on where the 2 pair go, it could give me different shapes, but I don't get to choose. We do exactly what the molecule does, and if there are 2 lone pair, they go exactly opposite each other. This gives them the most room. We just have to simply learn that they do, and so if there are 2 lone pair, then the remaining 4 atoms of the 6 around the center will take these 4 positions, and at this point we call this a square planar. All my angles here are 90 degrees, and so my molecular geometry would be a square planar in this case. I encourage you to put your hands on some models, either store-bought models or marshmallows and toothpicks, and try these out.